Okay, good afternoon, ladies and gentlemen. For those of you who do not know me, I'm Norman Howell. I'm the CEO of the Pipeline Industries Guild, and I will be your moderator for today's webinar. I'd like to welcome you all to this inaugural webinar of the Green Alliance. And the Green Alliance is a partnership between the UKSTT and the Pipeline Industries Guild, and we've joined forces to explore, share and promote industry's drive towards net zero emissions and reductions in the environmental impact that they make. For those of you who are not familiar with the Guild and UKSTT, I'd first like to introduce them to you. The Guild's key objectives are to promote pipelines, connect people and advance pipeline technology. We provide a platform for all who are involved in the pipeline industry to share best practice and technological development. And the UKSTT is the only UK society dedicated to promoting the use of trenchless technologies for the installation and repair of underground utilities. And it looks to share an advanced knowledge and experience of using trenchless techniques to provide a more efficient and environmentally friendly and cost-effective approach than using conventional open trench methods. Both organisations have a very diverse membership that includes network owners, contractors, consultants, equipment and material manufacturers and suppliers. We also have members of academia and also from support service providers such as environmentalists, health and safety specialists, etc. And throughout this year, the Green Alliance intends to hold a series of webinars leading up to a face-to-face seminar, which we're going to hold at No Dig Live, which is taking place in Peterborough between the 14th and 16th of September. So back to today's webinar, and today we're going to be focusing on introducing hydrogen to the gas networks, and we're also going to look at roadworks with robotics. Now, the introduction of hydrogen into the gas network is a key component of the UK's approach to achieving net zero by 2050. And something that surprised me, currently about 30% of the UK carbon emissions are from the heating of homes, businesses and industry. So to meet the government's net zero target, really a large scale conversion of the gas grid from natural gas to hydrogen is vital. So to look at this, and how this can be achieved, we've got two presentations today. Firstly, Ryan Smith, who's the NIA program lead at SGN and chair of the Pipeline Industries Guild Hydrogen Focus Group, will provide us with an overview of the UK hydrogen development landscape. And that will then be followed by Stephen Tomlinson, who's the SGN's H105 program lead, who'll be providing us with an overview of their H105 project and the part it can play to deliver net zero. And then after that, we'll move on and we'll look at some novel robotic technology. If you think about it, the inspection, maintenance, repair of underground pipeline and energy assets is an increasing problem in both having to try and gain safe access to them, as well as undertaking the work that that's needed to do the repairs in an acceptable and social and environmental manner. And it's probably getting on for 10 years ago now. We had the introduction of vacuum excavation and keyhole repair techniques for this type of work, and they've certainly resulted in less disruption to the public, an overall decrease in greenhouse gas emissions and a reduction in costs. So I'm looking forward today to seeing a further innovation in this area with a presentation on the development of robotic equipment, which will expand the capabilities of this system further. Dr. Ali Azmai, who is the head of AI and machine learning at UCL Technologies, and he's currently the project engineering lead for the robotic roadworks and excavation system, will be providing us with our third presentation on sustainable roadworks with robotics. Just to give you a few housekeeping rules for today, I'd like to advise you that we will be hosting a question and answer session after we've heard all three presentations. So I'd like to ask you if you could post any questions that you may have within the questions function on the GoTo platform. Also, I'd like to make you aware that this webinar is being recorded and it will be available to view in a couple of days' time on the Guild and UKSTT YouTube channels. So without further ado, I'd like now to ask Ryan to deliver his presentation on the UK hydrogen development landscape. So over to you, Ryan. Thank you.
Okay, thanks, Norman. Appreciate that. I'll just get my slides up. That's okay. Hopefully everybody can see my slides now. Yeah, so thanks for the introduction, Norman. So my name is Ryan Smith, Network Innovation Allowance Lead at SGN. So I've worked in the innovation space for a while now. Previous to that, primarily technical compliance, engineering policy. So today I'm just going to talk about, just give you a very high level overview of the kind of UK hydrogen development landscape and some of the key priorities we're looking at this point in time. Obviously, Norman mentioned the focus on decarbonisation and net zero, so I'm going to touch on some of that today. Really, today what I'm just going to run through is some of the key policy changes that we have now and are coming in terms of the ask of what is net zero, how can we achieve this, and reference that against actually the challenge of achieving net zero, just how big it is, some of the strategies that we're developing to deliver on that challenge, and talk about GD2. So GD2 from a gas distribution networks point of view is the regulatory framework period we're in just now. So it just started in April there, and it's a 5-year block of time that we're funded to deliver a number of key objectives over that regulatory period. So I'll just go on to, in terms of the policy landscape, there's been a lot of work done in this area and a lot of drivers in this space. So we've got lots of things from the UK heat policy decision, which is coming in 2025, but in order to map the landscape to that, regional governments and sort of devolved governments and the UK as a whole, we've tried to pull together what is a route map effectively for net zero and just how we can achieve this. There's also been lots of work done through BEIS with regards to white papers around that, the goal of hydrogen and how we can decarbonise energy for UK PLC. So these are freely available, and you can get copies of them on regional government websites and the main Gov website in terms of if you go into the energy policy section of the website. So in terms of heat decarbonisation, again, Norman touched on this, and it's quite a busy slide, but it's quite an important slide really in terms of what gas is and what impact it has on the environment and ultimately why we need to change. So, you know, as Norman mentioned at the start there, so 40% of effectively carbon emissions really comes from heat from the gas side of things. So really that's for heating your homes. There's industrial processes, so cooking, hot water, all those things. So 85% of homes in the UK obviously have gas supplies, and that's the population of people that's using it. So when you look at this, the graph on the side is a representative volume of energy. So this chart was taken from daily consumption rates from when we had Beast to the East back in 2018. So in terms of building networks and having capacity in your systems, we have to design these systems based on what we call a 1 in 20 scenario. So it has to be suitable capacity to ensure that we can manage and infrastructure can keep on going in a 1 in 20 scenario in terms of demand conditions. So even in scale of energy that was consumed in the UK on, I think that was, what date was that? That was the 1st of March. So that was the peak day in a peak 20-year period. And the grey is the spike period is obviously gas reference and the consumption of electricity there. So within that as well, like the gas itself delivers far more energy than electricity to homes and industry and various other applications. I think what's also important to note is that the actual electricity that's getting consumed as well, so that the red spike, a lot of that electricity actually comes from gas. So just before the webinar call, I've just modified my slides slightly. So even today, as we are today, it's a relatively mild day, well, certainly for Scotland because the sun's shining, so that makes a change. But so even today with relatively mild temperatures, it's not everybody's not got their heating on, we're still consuming up to, I think it's 38% of generation for electricity is still coming from gas. Now, I generally watch this chart on a daily basis, and I've seen it go up right up into the sort of high 80s, early 90s on really peak days in the winter. But generally, on a cold snap period, that can sit about 70%. So in terms of the challenge for gas, it's quite significant, and how that translates into UK energy policy is pretty significant as well, because without gas, then you can't just remove it and expect everybody to go about their business as usual, because subsequently there's not enough energy supply in the UK for our consumption needs. So really, in terms of the net zero and the challenge of all that, where we're actually going at the moment. So as I mentioned there, the 2025 policy change is critical. That's a key lever in terms of the decarbonisation route map for gas generally. So as of 2025, when we get the heat policy decision, so we're really in that red critical period in terms of the direction of travel. So we're really all about identifying evidence and the case for hydrogen through our pipelines. So when I'm talking about pipelines, I'm talking from your transmission right down to distribution. So the full range of that, and obviously the other elements that that's incorporating. So really, it's a critical path, and we have to do a lot of work in the next 5 years really to identify and evidence out exactly what we can achieve for hydrogen in a relatively short period of time, to ensure that the heat policy decision that's made is actually suitable with the networks themselves. So really, the ideal path is where it goes off there into the pathway to net zero, where we've got full hydrogen economy, various options for power and industry, and basically it maintains and unlocks the asset potential of pipelines that we've currently got. If it goes the other way, then there is still route maps where pipelines are still be applicable to transport and energy needs to the UK. But of course, we're in then of how do we then heat homes? Is it an electrification solution? How do we do that? That becomes a significant challenge for the electricity grids, and an economic challenge as well, in terms of how are you going to fully electrify the UK and the cost involved with that. So as you've seen in the last slide, gas network deliver 4 times as much energy to end consumers. So you're going to have to reinforce or build 4 effectively transportation grids for electricity overlaid on the existing infrastructure. So it is a real challenge if electrification is the route. Within that, we're still looking at options that if gas for homes is not going to be viable options, and we're looking at hydrogen solution, which is the viable option, then we may go down the road of hydrogen for transport and power, or hydrogen for industry as well. But that critical path ultimately, if we don't achieve the work that we need to do in the next 5 years for that critical 2025 heat policy decisions, we're kind of looking at the track end of the line in terms of decommissioning as to where we go with pipelines technology. So it is a pretty serious point and really time critical as we currently sit at the moment. So, I don't want to scare anyone, but in terms of referencing that, so actually in terms of support from government and industry, And really what we're looking at in the next 5-year period, we've been allocated a significant funding framework whereby we can actually utilise this funding to demonstrate the case and provide the justification of hydrogen being the viable energy path for UK. So I'm not going to go through the table there, but as you can see from there, there's significant funding mechanisms being made available to the networks to utilise to demonstrate the safety case and the technical case that hydrogen is fit for purpose for the future. Within that as well, I think that everybody now moving forward, we're actually into a space where we're looking at whole systems. So whole systems can be quite complicated, but really within SGN, when we've set up a whole systems charter, so really it's not necessarily about gas distribution networks and electricity distribution networks. It's really about the overall energy system as a whole and regionally what you can actually do with that. So for instance, you could use hydrogen as a storage medium where you're generating a lot of wind power, but you've not got the peak on the network to absorb that wind energy into the electric grid, so you can convert that into hydrogen as a storage medium and then convert it back in as a power option. So whole systems is really about that, is the interoperability between the gas and electricity networks. And really what that, when you look at that as a system map, it does get quite complicated and there's lots of crossovers and things, but really I just want to explain that that system as a whole really looks at regional options across the UK as to where, for instance, strong or weak parts of individual networks, whether it's gas or electricity, how can those complement each other and effectively distribute the energy in a more even and suitable way, certainly over peaks. So we're kind of pooling resource to actually to deliver energy to the consumer that ultimately is going to meet the requirements of net zero. I've added an element of East Fife there. So really, I know Stephen's going to talk about the H100 that feeds into that whole systems approach for that regional area, but I'm not going to still stand and talk about that too much. So really in terms of where I am at the moment, I'll just in summary. So really in terms of the policy for us, ultimately it's about securing the assets for the future in terms of pipelines. So obviously that's to achieve net zero. But the challenge itself is developing that credible route path to net zero. And the strategy is about how do we actually do that. So it's evidence in that pathway to ensure that we are hydrogen ready ultimately. There's a successive plan in place. And when we look at that, the customer is at the heart of this. So regardless of its gas or electricity solutions for regional areas, it's the best solution that fits for the customer. I know I've zoomed through that pretty quickly, but ultimately, if you want to read up on that, there's a lot of resources available on the ENA website. So if you are interested in the topic, I suggest that you maybe go into the link there and read up on some of these key, I suppose, government policies and some of the work that individually the networks have been doing and collaboratively overall in terms of the energy strategy for UK, certainly for the next 5 years. And on that, I'll say thank you and I'll pass you over to Stephen.
Okay, thank you, Ryan. And you've set the scene very well there. And as I mentioned earlier, we will be taking questions at the end after the 3 presentations. So please use the questions function on the GoToWeb platform for any questions that you have. So now I'd like to move on and invite Stephen to deliver his presentation on SGN's H100 5 project and the part it can play in delivering net zero. So over to you, Stephen. Thank you.
Thank you, Norman. I will just share my screen. Hopefully that's showing correctly for everyone.
You just need to put it into presentation mode. Perfect.
Okay, thank you. So yeah, thanks for that, and thanks Ryan. And yeah, I'm Stephen Tomlinson, H100 5 program lead working for SGN's Energy Futures team, and as introduced, I'll be talking to you about our H100 project, which is a world first end-to-end system delivering hydrogen for heat. So context has already been provided by Ryan in more detail, but just in general and how the context sits for this project. So as mentioned, the UK government and the Scottish government have their targets set for our legislation in place, in fact, for net zero 2050 in the UK and 2045 in Scotland. As also mentioned, heat accounts for a third of the load, domestic heat. So clearly decarbonising the gas network is required in order to meet net zero. And hydrogen is widely recognised now as a credible alternative to natural gas, as it delivers the same benefits of a gas without the negative impacts of impact on the environment. So the gas quality decarbonation pathway shown there, we developed this some time back, and that's now been adopted by the other GDNs, and working with BEIS has been rebranded as what we call Gas Goes Green. Gas Goes Green is a program or a pathway that incorporates all the various different programs, such as our H100 program and H21's programs and the other GDNs and BEIS's Hyper Heat program, into an overall program that delivers hydrogen town in 10 years' time, and that's now sort of incorporated into the 10-point plan announced by the UK government last year. And on that pathway, H100 Fife is recognised as a critical national project, so it's really the first step on the way towards net zero and demonstrating hydrogen for heat as a credible option, and towards the first hydrogen town. And as Ryan's mentioned, heat policy decisions are expected in 2025, or what we're told officially is this decade. We believe it's 2025, and what we hope our project does is it sets hydrogen in a good place in advance of that heat policy decision. And the ultimate goal for us in terms of what is within that policy is that hydrogen boilers are mandated in a similar way to digital ready TVs were mandated some time ago, and that obviously will stimulate the market and ease the transition if hydrogen's the course we're going to take. So I did have a video I was hoping to show, but we tested it out, it didn't work. But if I can point you towards our website, which you can see that animation on, and also other information about the project, that link's at the bottom of this slide. It's just a 3-minute video, an animation that gives an overview of the project. So the overall system, which is depicted here in this diagram, starting on the left, we have our offshore wind turbine, which is already in place. That feeds power to our electrolyser, which we are in the process of procuring at present, so I don't have details of what exact type that will be, but electrolysers in general, they take electricity in and they produce oxygen and hydrogen. We are going to be storing that hydrogen in high pressure bullets, as they're known, or storage tanks, above ground steel tanks. That amount of storage is sized so as to provide 5 days of the peak 1 in 20 demand storage, and that's to allow for security of supply and to give us time to rectify any issues that we might encounter. We also have a backup electricity supply should the wind turbine not function or the wind doesn't blow. That hydrogen then reduced in pressure, and it will be transported through our new PE distribution network, which is a low pressure 75 millibar and below distribution network, and that network will pass 1,000 homes. The whole system sized for 1,000 homes, but we in this phase will be connecting 300 homes to our new system, and those homes will then be supplied with hydrogen appliances. The project's planned to run for 5 years, or 4.5 years, but 5 winters, and that gives us a good amount of data gathering and an understanding of the operation of the system. The distribution network will be laid in parallel to an existing gas network. It's a gas network area already, and that gives us key learning as we can switch people from gas to hydrogen. So people are already used to gas, and then we can learn what they think is different, if anything, to powering or supplying their house with hydrogen. The other thing we have on site is our hydrogen demonstration facility, which I'll talk about in a bit more detail. But really, that's a key customer engagement tool that we're using to recruit, for want of a better word, our 300 homes into the system. All the people on the demonstration will opt into it. No one's going to be forced onto this demonstration. And really, the reason that we know we are ready to commence a trial is because of the amount of work that's been undertaken already by us and other programs, including the ones mentioned previously and shown on the right there. And these programs have done all this sort of safety and evidentiary work that we need in order to know that we can now move on to the demonstration phase. This being the sort of catchphrase we often use, it's not a trial for safety, it's a safe trial. And the reason we know it's safe is because of what's depicted here. So we've done work on flame visibility. That's a commonly heard thing, that hydrogen burns with an invisible flame. But in the real world, really, when there's all sorts of contaminants and any ignited gas leak, for example, isn't going to be invisible, or the risk, the price to mitigate that risk is not reasonable. So we've worked on that. All of our procedures have been looked at, and training packs and operating procedures have been developed. We've done work with our project partners on materials and jointing for PE networks, and we now understand that the existing PE pipe and construction techniques as used for natural gas are also suitable for hydrogen. Things like permeation and the likes aren't an issue or not a major issue. In fact, on permeation, a hydrogen molecule is only about 3/4 the size of a natural gas molecule or a methane molecule, so it's not really much smaller in molecular terms. We've looked at odorant. We know that's suitable on the existing gas system, leak detection, and also we've had everything we've looked at reviewed academically, and as I say, we now know we're ready to commence. The other thing we've had a good look at is commercial and regulatory models, and I'll touch on them again in a bit. So here we have the actual site in Leavenmouth in Fife, next to the town of Methil. This is the Energy Park Fife, where we're going to be building our plant. It's a yard that's been known for energy for some time. It used to be involved with the coal industry, and recently it's been an energy park, and that's why this demonstration 7 megawatt turbine is there. That's an actual offshore turbine on the right hand side, although it's not really very offshore. It is constructed in exactly the same way. Our site is this light brown edged with blue area. That's where we're building our demonstration facility, our electrolyser plant, and our gas storage, etc. And then the shaded area of houses is where we're going to be building our new network area. As I say, that's laid in parallel to an existing gas network, and that provides us with key learning opportunities such as customer choice, opting in, opting out, as well as opting out as well. So anyone that wants to leave the project can do so and return back to natural gas supply. So we're currently in planning determination for our site, and this is the site plan layout that's gone into planning. As you enter the site, as you look at this, it's not orientated north, but as you look at this on the right hand side, you enter the site, that first thing you see is the demonstration facility, which is really 3 terrace properties that are made in the sort of spirit of the housing stock in the area. So that means customers can come and see and feel and look at hydrogen in action. And then the central property is also a sort of demonstration home, but it's also one that we can use as a in a more formal sort of setting and provide presentations and classroom events and things and education on hydrogen. Moving around the road there to, I don't know if you can see my mouse, but right in the middle of the picture, that's the electrolyser, which is indicative at this stage because, as I say, we haven't chosen one. That's just the largest footprint technology, a control room, and then excuse me, and then beyond that, or above that pink line, which is the route of the electricity cable, is our gas side, and that's got the 6 storage tanks and the PRS odorant unit, and then that's going to feed a network up to the top of this picture, which is sort of northwest of the site, as shown previously. And then just that inset image on the top right, I've included that because that shows you how much spare ground we have on the site that we are leasing, and that is deliberate so that we have expansion opportunities. So if we go beyond phase 1 of heat policy decision, does as we hope, we can then expand the network out to more in the 1,000 networks homes area and then even beyond there, and that gives us room for more storage and other things that we're planning on implementing. So just some pictures here of sorts of components you might see on site. On the left-hand side is one of the electrolyser technologies, which is housed in shipping containers. And then on the right-hand side, we've also got some of the steel bullets or steel tanks. And behind that is a housing for the other type of electrolyser technology that we might end up purchasing, which was actually the one shown in the planning. Network area itself, so it's 8 kilometres of a new PE network, all in all. Sized, it's as I say, it's constructed, or it will be constructed in exactly the same way from exactly the same materials as we use in the currently in the PE distribution networks. It's sized for the whole 1,000 homes area, but in this stage we're going to be connecting 300. 300 is the number determined because beyond 300 we have a statistically representative number that we can learn from going forward, and it's going to shape the overall rollout of housing if that were to be the successful outcome. We've had some visualizations done. So this is looking from the wind turbine back towards the site and to the town of Methil in the background. You can see on the left the storage tanks, the electrolyser building on the right hand side there, and then just peeking out beside that is the demo facility. And then just where that bus is something called the viewing platform that was built for the energy park. And the other view we've had done is from there looking down onto the site. So from here you can see the wind turbine. On the right hand side you can see the storage and the PRS, etc. The gas side, electrolyser in the middle, and then on the left hand side is our 3 demo facility terraced houses. And just moving on from that into the demonstration facility, and the real purpose of that is this customer engagement tool. And the point of the demonstration facility is that we can build customer confidence and have people over to see and understand hydrogen in action in advance of them signing up to opt into the project. So our customer model, the customer-centric model, is that they're cost neutral for them to participate, and we're doing that in a number of ways. In our regulatory model, we're keeping their bills the same as they currently have, and we're providing them with free appliances, like-for-like appliances for their gas ones, and free maintenance throughout the trial. So we really don't want to over-incentivize customers to join, but we also don't want to make it cost prohibitive for them. So we're striving to be cost neutral for them, so that any outputs we get from them and all the learning we get is unbiased. So the way that we have managed to make the customers not be disadvantaged in terms of cost or supply is via our regulatory model, which I'm trying to depict on this slide. It's quite complicated. We've had to develop a new business as a delivery vehicle called SDN Futures, because our existing gas distribution license won't allow us to be a gas producer. But likewise, our new entities is not allowed to transport gas. So both SDN Futures and the current SDN have to work in parallel to deliver this project. And really what we're doing is we're producing hydrogen, which is quite a high cost to produce relative to natural gas at this point. So we're selling that at a loss to a third-party shipper, and that loss is being borne by the project. And that means that shipper can then supply the gas down the supply chain as normal, meaning that the customers at the end of it don't see an increase in their bills. And we're managing to support that by working in the background with the operators of the billing system to ensure that the right triggers and flags are in there. So it's quite complicated, and it could well be a model for rolling out hydrogen going forward if it's successful. So it's another thing that we've developed and we're implementing that should help and support moving onto a hydrogen model. Quickly on programme, in the purple bars here is our project elements, and then below that we have the key activities, which are colour coded by funder. The funding of the project is quite complex as well, but it really involves ourselves and the Scottish Government in the form of a grant purchasing the electrolyser equipment and storage tanks, and then the rest of it's been funded under Ofgem under its NIC mechanism. And that NIC mechanism just started at the start of April. We're now moving into that and moving into the pre-construction phase, where we're getting the designs detailed out. We're completing the cases for safety in preparation for construction in 2022, and then in operation from 2023 to 27. So, as Ryan said, there is a reason that we picked Fife. There's a reason the project's called H100 Fife, because the Fife wasn't the only location that we looked at. We had three locations, one in Aberdeen, one in Machrihanish in Argyll and Bute, and then Leavenmouth in Fife. For various reasons, we have landed on Fife, and that's largely in part though due to the expansion opportunities and what's nearby. That's really shown in these phases here. So we have phase 1 as described, which is 300 homes and a new network. Phase 2 will involve more homes within that network and some conversion onto the hydrogen network from the existing gas network, sorry. And then 3 and 4 is further down the line, and that's looking at industrial and commercial and transport, and then eventually the whole system, which Ryan touched on. And as I say, this area was selected because of its suitability to a whole system model. And then just this last slide is the outcomes that we hope to gain from the project. As I say, it's all gearing towards demonstrating hydrogen as a credible vector to carry energy around our gas network by 2025. But in doing that, we'll get lots of learning for overall system transformation. One of the key things that we'll get out of it is that because we are building this as an EP network with the same construction techniques as normal, that means that because 80% of the current GB network, which is 280,000 kilometres, is PE, we're really validating that as suitable in the large part for hydrogen, just by doing this project. So it's really quite key to the overall evidence base. We're also, and one of the real challenges outside of the technical challenges is bringing people along the journey and making sure customers accept and want to switch their energy from natural gas to hydrogen. And that's something that we're going to get a lot of learning out here because of our opt-in model and our opt-out model. if we were to jump straight to a conversion, say for example, we wouldn't get the same learning because people would be asked to either take hydrogen or to change their fuel source from natural gas. But here we get real learning and unbiased learning. And then there's a few other points there that I'm not going to read them all out, but statistically significant and scalable is a key one. As I said, we've got 300 homes for a reason. That should be able to scale up and give us a key amount of understanding going forward. And then regulatory models that we're implementing and commercial models all are replicable and expandable. And finally, market creation, which is really the heat policy decision going the right way is needed for that, but also what we're doing in these trials and other trials on the pathway are all helping stimulate the market and drive down costs. So that's really me. That's it abruptly ended. So hopefully that's been useful to you, and happy to answer any questions. Thank you.
Okay, thank you, Stephen. That was really quite fascinating, and it's really interesting to see the work that's being done to drive the hydrogen rollout. So yeah, very interesting. Again, we have got a couple of questions in our question function, but I'm going to save those till the end. And if anybody has any more questions, please place them in that question function, and then we can we can gain those answers at the end of our next presentation. So thanks again, Stephen. And I'd now like to move on, and we're joined from the States by Dr. Ali Asmari, and Ali has an MS in robotics and automation and a PhD in mechanical engineering with specialization in computer vision and machine learning from Oklahoma State University. And then prior to joining ULC, Ali has over 15 years experience in the field of robotics and has led projects in diverse sets of industries. So I'd now like to invite Ali to deliver his presentation on sustainable roadworks with robotics. So over to you, Ali. Thank you.
Thank you very much, and good afternoon, everyone. Today I want to talk about robotic roadworks and excavation system. It's a robotic platform that we have developed in the past 3 years in collaboration with SGN. This is a project that was funded by Ofgem, and the idea was really to create an autonomous system that can carry out excavation operation from beginning to an end. There's a lot of challenges associated with the traditional methods of excavation, and then talking about Green Alliance and the ideas of replacing the network or adding hydrogen to the network. There's a lot of inspection and work that needs to be carried out, and it is necessary to have the right tools when we are upgrading networks at this scale. So I'm going to walk you through some of the development that we have done and achievements that we have been able to get to, and also the future of what we're planning to do with this robotic system in the UK. Just a quick introduction on ULC Technologies. We are a robotics company in Long Island, New York, and we're really specialized in developing customized platforms for different industries, depending on the need of our partners, who are usually companies within energy industry. We develop platforms that crawl inside the pipe, crawl over cables, or fly around assets to do inspection. And one of the recent projects that we did in collaboration with SGN was the robotic roadwork and excavation system. So our business model really is to, through different stages of R&D, develop these prototype solutions, and then collaborate with our partners to provide these solutions as a service. to potentially tackle some of the challenges that they have in their day-to-day operation. Now to robotic roadworks and excavation system. Really, the idea behind this system is to create an autonomous system that can carry out the excavation operation. And this slide really talks about the main challenges associated with the way traditional excavation is carried out right now. As you might know, there are millions of excavation operations just within the United Kingdom that carried out on different areas. And just because of the risky environment that these operations are usually taking place, a lot of these methods that are being used right now are heavily manual. And that means operators with very traditional techniques like shovels and jackhammers breaking the road surface and trying to expose the assets that are under the ground. You can imagine exposing the operators to this kind of like a risky environment and the safety challenges associated with that. Then there's risk of damaging third-party assets. Just because there are not that many accurate maps of the assets under the ground available, and also just some of this infrastructure is really old. There are not that many information stored when they were laid down under the ground. It makes it very difficult to avoid damages to third-party assets. So as an example, when excavation is happening to expose a gas pipe, on the way to get to the gas pipe, there's going to be a lot of electric cables, fiber optic cables, and things like that. They can potentially get harmed throughout the operation unintentionally. Now, that's one part of the challenge, is all the risks associated with causing damages to the network. But then the entire operation as a whole is not very efficient. As you might know, an excavation operation involves different crews with different equipment going to a specific site and carrying out different pieces of the operation, from identifying where the assets are to breaking the road surface, excavation and exposing the assets, and then carrying out operation on the assets and then reinstatement. This can involve 4 or 5 different crews that come to the site throughout the entire life cycle of that excavation operation. And just because of this disconnect, there's a lot of inefficiencies associated with extra equipment coming to the site, extra teams coming, and miscommunication and the gaps that exist in between. And then all of this heavy equipment that are used for this type of excavation have a huge CO2 footprint, which also another big challenge, especially with the goal of achieving net zero. As you might know and you have experienced, every time there is an excavation in the area, there's huge disruption to the public, the road closures. And just because the traditional methods of carrying out these excavation operations take a lot of space, to give access to human operators to go far enough down to get to, for example, a gas pipe to carry out a maintenance operation, a large area needs to be exposed. A large excavation area needs to be cut in the road surface, and that creates even a larger disruption to the public. So with all of these challenges, we set a very ambitious goal of developing an autonomous system that can carry out the entire operation from beginning to an end autonomously in one kind of like a job site deployment, from starting from below ground sensing to identify where the locations of the assets are, and then cutting the road surface and removing the topsoil, whereas usually like concrete or asphalt top layers, and then excavating the soil that's above the assets and removing that, carrying out operations on the assets once they're exposed, and then backfilling and reinstating the road. Our goal was to develop a robotic system that can do every step of this operation autonomously, again, in one deployment. So this is kind of like the base of the robotic roadworks and excavation system. It's an open source robotic platform. What we have done is we brought in a 6 degree of freedom robotic arm to the day-to-day environment for operations. We put it on tracks, and this is also an electric vehicle, so we have battery compartments within the system and all the electronic control necessary for carrying out the operation. Now, the system is designed with an open source mindset, so different tools and end effectors can be integrated into this robotic arm, so different types of operation can be done with one platform. Again, the idea was to create specific tools that can start the operation, that can expose the assets, and then later create this opportunity for other developers to come in and create different tools based on their needs to carry out operations on other assets like electric network or water network. Now, before getting into the, I have some videos of the operation of the robot, but since we were talking about carbon footprint, I wanted to touch on the electric aspect of this system. What we have designed here is a fully electric system, completely untethered, independent of any support group, that can go for long distances to a specific job site and then provide enough power to all the components necessary for doing this very heavy-duty construction work. On board of the robot, we have 16 independent batteries, total of generating 35 kilowatt hour. The batteries that we have put on this robot are lithium iron phosphate. So this is kind of like the latest technology in the battery system that allows us to optimize the charging cycle and using of these power system. On board we have, so these batteries are all DC powered, and then when we were talking about like robotic arms, massive electric motors that are driving or carrying heavy payload like a 200 kilogram core that's been taken out of the road surface. To articulate that, you need a substantial amount of power, and usually these robotic arms, especially the one that we have used for this design of this system, requires 3-phase AC. So on board of the system, we have included inverters that turn that DC into 3-phase AC necessary for our operation, and we're able to carry out 8 hours of non-stop operation. This can include multiple keyholes and operations on different assets at a job site. So here I'm going to jump into like different aspects of the operation for this robot with some videos. The first step of the our operation is below ground sensing. As I mentioned, there are usually not that many accurate maps available of where the assets are under the ground, and usually mark out operation is one of the necessary steps to be done before any excavation. A crew comes into the site with a lot of sensors, some of them that are more progressive bring a EM sensor like a CAT and Genie, or some companies might bring up a ground penetrating radar for scanning. What we have done here is we have integrated multiple sensors within one sensor suite. In this case is a ground penetrating radar and EM sensor. And then the robot picks up that sensor package and carries out the same type of operation that operators are doing manually at the job site, but now with a very high precision and accuracy of a 6 degree of freedom robotic arm, where you see in a factory environment doing, for example, welding or assembly of components. Now, this precision and accuracy allows us to increase the resolution of the data that we are collecting. So if you want to compare to a traditional method, typically operators do this scanning every foot, like every 30 to 25 to 30 centimeters. But what this robot is able to do is we can do scans about 25 millimeters apart. And that high of a resolution data collection allows us to create a very accurate map of the assets under the ground. So this was a time-lapse video of the robot in action collecting this data autonomously. The data collection takes about 5 to 10 minutes. Once that's done, on the spot, the robot autonomously processes all the results and then create a 3D point cloud of the locations of the assets that are under the ground. What you see in the video is the user interface that we have created for an operator off-site that can remotely communicate with the robot and see everything that the robot has collected. So there's a yellow box that shows the area that was just scanned with the robot. And then under the ground, you see the point cloud of the assets that has been identified using this data collection and processing. Now, throughout the tools that we have provided for our operators, the operator can go through and filter out noise from this and then identify exactly what is under the ground. Again, this is very high resolution, dense point cloud. So the operator can almost like rotate everything in kind of like a 3D environment. And what you see in this video is a very clear representation of a pipe that's almost like perpendicular to the orientation of the robot, and then 3 other pipes that are crossing over that pipe. And using this 3D point cloud, now the operator can very accurately identify what is the best spot for excavation to expose the specific asset that they're looking for, and also try to find that, identify or pick that spot properly, so throughout the excavation operation they don't bump into any other third-party assets that might be around the vicinity of excavation area. So after sensing is completed, the 3D point cloud is generated. The robot drops off the sensor package and then picks up another tool for excavation. Before that, using that 3D environment, the operator can identify the best location for excavation. So here, what you see in this user interface is the operator is moving that cylindrical form, that green cylinder, around to identify the best location to cut that core out of the road surface. Once that core is properly selected, now everything is within the working boundary of the robotic arm. So the robot has the same coordinate system for everything. After data collection is completed and processing is done, the robot drops off the sensor package and picks up another tool to remove a pilot hole from the road surface. The cart, the aluminum frame cart that you see attached to the robot, is basically a tool cart that carries different tools for specific operations. The operators manually bring these tool carts on the side of the robot, and from that point on, the robot autonomously detects where each tool that it needs for completing its operations are, pick up the right tool, and carries out the operation. So in this case, the first step is cutting a pilot hole from the road surface. The tool is picked up autonomously, and now it goes to that specific spot that the operator selected using the 3D point cloud generated from below ground sensing. In this operation, the robot is using a very accurate force sensing. So it measures the amount of downward force that applied on the road surface. And as soon as it goes through the top layer, it immediately senses the lack of resistance and then pulls out the core, pulls out the pilot hole out of the ground. Then that tool is put back into the cart, and then the robot picks up the next tool for cutting the core out of the road surface. The goal of this operation is, instead of doing a massive excavation, to do a keyhole excavation, and through a small 600 millimeter core, the robot will be able to articulate different tools and carry out all these necessary inspection or repair operation on the assets that are exposed. So the core drill is dropped off, and then the next step is picking up the next tool for cutting that core. In this case, we have designed a custom chainsaw. It's an electric chainsaw, much more powerful than the typical concrete cutting chainsaw for cutting the road surface. So this tool allows the robot to cut up to 14 inches of reinforced concrete or asphalt. The other thing I need to mention is there's an autonomous tool changer at the end effector of the robotic arm that allows the tool to very easily, very quickly bind with different tools. And through that tool changer, different type of command or power, or in this case, the cutting the road surface, water is provided to the tool. So through that big black hose that you see wrapped around the robotic arm, power to this chainsaw is provided. Commands to different actuators on board of this tool are provided. And also fresh water is being pumped through there, going and cooling off the motor that's on board of the chainsaw. And then at the end, the water is used to cool off the cutting blades on the chain. Now, what you see the operators are doing here, after every once in a while, they go and tighten the chain on the chainsaw. This is kind of like a 3 to 5 minute routine procedure that we carry out throughout this cut. Usually cutting so in this case, it's a 24-inch diameter core, about 600 millimeter core. And this core was about 35 centimeters in depth. So cutting a core of this size that weighs about 180 kilogram takes about 45 to 50 minutes for the robot. And the robot goes through a combination of different movements and procedure to cut this shape. So what you see here is the robot first did a bunch of plunges to detach the core from the rest of the road surface. And then it goes into a circular pattern, cleaning up the edges of the core. Once that's completed, it does some finishing plunge cuts, and all these plunge cuts are force controlled. So the robot applies the right amount of force to the road surface. And if the road surface is softer, it can carry out the operation so much faster. So we can speed up the robot. Again, everything is happening autonomously. Now, as you see in this video, the 6 degree of freedom of the robotic arm allows articulation of this tool very effectively, very easily, which helps us cut not just a round core out of the road surface, but different shapes and forms, like an oval cut, if we need to have more room around the asset when we are exposing it. These are all possible with just a little bit of programming on the robot side. Now, the core is completely cut using the chainsaw. So the robot drops off that core cutting tool and then picks up another tool that we've designed for extraction of the core out of the road surface. This is a pneumatic device that utilizes the pilot hole in the center of the core and allows the robot to grip on that core. Again, in this case, I mentioned it's about 180 kilogram weight. It pulls it out of the keyhole and puts it on the side of the road so that the next step of the operation, which is excavation, takes place. So that was cutting the road surface and removing the core. The next step is exposing the asset that's under the ground. So we have designed another tool that utilizes supersonic air. It basically turns compressed air into supersonic speed and pressure, and then blasts the soil with this highly pressurized, fast pockets of air, agitates the soil, pulverize it, and then using vacuum excavation, we remove everything that's been agitated and pulverized. So again, the robot picked up that tool. This is relatively larger, allows the robot to dig up to 7 feet deep into the ground. And then it brings a tool down for our operators to attach an adapter that basically connects this tool head to a regular VACX system that can be brought to the site. Now, this VACX unit will be utilized to remove all the agitated soil. Another thing I want to mention is the videos that you are watching are from a live field trial that we carried out. Because of COVID, we couldn't bring the robot to the UK. So what we did is we did a field trial in the US, and then we kind of like broadcasted everything live for our partner SGN and Ofgem to see everything in action. So this is the next step of the operation. We're using supersonic air nozzles, blasting the soil, agitating the soil, and then the vacuum hose in the center removes the dirt that has been agitated. That cover, the Cartesian platform that you see in front of the robot, is a cover that we put our operators put down to basically protect any loose material after being exposed to like this highly compressed air to go around and hit somebody. So this is kind of like a covering in that excavation zone. So everything is contained. The entire soil that's being agitated and removed is contained. And again, the robot is going through this fully autonomous operation until it achieves the depth that the operator has defined for the excavation through that user interface that I showed you earlier. So once the excavation is completed, the robotic arm pulls the tool out of the cart. And once we open up the excavation site, you can see the two pipes that are exposed in the bottom of that keyhole. These are the crossing of the two pipe that was initially detected through sensing and then selected by the operator as the best location for excavation. And then once the excavation is completed, you can see that that crossing of the pipes are exposed. So the pipe is exposed, and then the next step is carrying out operation on the pipe. Here is a video of a tool that we have designed that preps a plastic pipe for installation of an electrofusion pipe. Again, going back to the reasons that we built this robotic system was to create an open source platform that can carry out this very accurate, precise work on any type of assets after doing the excavation. So once the excavation is completed, here is an example tool that we have developed that can carry out an operation on a gas pipe. And this is kind of like the proof of that concept. What you see here is an autonomous peeler device. What this system is doing is it's basically shaves off the surface of that plastic pipe and removes layer by layer that material, prepping the surface for electrofusion of a fitting onto the pipe. Now, in this specific design, we have utilized only pneumatic actuators. So all of the tools that we have developed are intrinsically safe, working around potentially hazardous environments, especially in this case, gas. So using all the pneumatic motors and actuators, what this tool head is doing is it clamps up on the pipe, shaves off the surface of the pipe, and then once it's completed, this operation takes about 10 to 15 minutes. Now, this can be done in the bottom of a keyhole and prep the surface like what you see in this video. Once that's done, we have developed another tool that allows the operators to install a fitting on the pipe. So the robot has this extended tool head that brings the end effector to an operator for insertion of an electrofusion fitting. So our operator puts in the electrofusion fitting, and then using the interface that's available, they plug in both the leads on this electrofusion piece, and then the robot actually powers up the tool to heat it up, and then that fitting will bond with the pipe that's been prepped for this operation. Once all the step of the operation is completed, I mean, the operator has inserted the fitting into the end effector. The robot autonomously descends the fitting down inside the keyhole over the pipe, and then it's using a force sensing method and applies a constant downward force according to the specification defined by the manufacturer of these tools. So what the robot is doing is slowly descending this fitting down until it binds with the pipe and then powers up the leads on both ends of the fitting. So the fitting is now heated up and it's bonding with that plastic pipe. And once that procedure is completed and all the requirements are met, the tool opens up and the robotic arm pulls the tool out of the keyhole. And that's the end of the operation on the asset, which in this case was installation of a fitting. Now, there are other things that can be done, like putting, for example, a saddle over the pipe, or potentially carrying out a different type of operation on electric pipe. Now, very quickly, the last step of the operation after the asset is exposed, the work on the asset is completed, the robot picks up another tool, in this case is a pneumatic compactor, that compacts the recycled material into the keyhole, prepping it for reinstatement of the core. So what our operators are doing, they're manually bringing in recycled material and dumping it layer by layer into that keyhole. And the robot goes through this, again, autonomous operation, compacting the soil layer by layer until it achieves the level of compactness set by the operators. As these layers are put in, the robot compacts them until it gets to the very, very top layer of the soil. And once the level of required level of compactness is achieved, the robot drops off that tool and picks up the next tool, which is the same tool that was used to pull out the core from the road surface. Right there, the tool is picked up, and then the robot autonomously goes to the same spot that the core was initially dropped off, pick it up from that location, and bring it and drop it off for reinstatement. Now I have to mention, this is a 180 kilogram core, relatively large, and there is a finesse in how to put this core back into the keyhole. The weight distribution is always, it's not going to be homogeneous around the entire volume of the core. So what the robot is doing is it's autonomously going in a circular pattern, identifying what is the best angle to push this core down. And every time it makes small adjustments until the core easily fits in back into the same spot that it was taken out of. And here it's put back in its place. Now I have to mention, this road surface had a 3 inches of asphalt on top. That core, the asphalt core, came out as a separate piece. So after dropping off the concrete, the robot picked up the asphalt, which in this case, the asphalt piece was so light that our operators just manually brought that asphalt core and put it on top. So that's the end of the operation. End to end, you saw it from scanning and identifying where the assets are till cutting the road, and then excavation, exposing the assets, working on it, and then at the very end, reinstatement. So what's the roadmap? Where are we going from this? Now that this robotic platform is completed, everything is tested and validated, we are shipping the robot to the UK very soon, and we're going to start field trials in the UK. We're going to be engaging with industry experts to identify other applications that this robotic platform can be very beneficial in. And then throughout this process, we're going to, in general, SGN has a vision toward upscaling the workforce and bring in new talents that can kind of like assist with the further development of this system. And then increasing the autonomy of all of these operations, adding more and more steps to the operation to make it more and more autonomous. As we mentioned before, this is an open source platform designed that it can potentially provide services to not just gas network, but other utility companies as well. So this is a multi-utility and cross-industry system. And eventually the goal is to increase the safety of operatives, reduce disruption to public, and also support the net zero strategy. Thank you very much. If you have any questions, I'll stay at the end. And also those 2 email addresses is if you want to send us any inquiries or want to get more information about this system.
Okay, thank you, Ali. That was really very interesting, and it's great to see, having in my life started off introducing trenchless technology maybe 40 years ago, to see how things have developed and how robotics have moved in. And I think it's it is the future, and it's great to see this innovation. Thank you so much. Apologies, I seem to have got myself muted there. If I'd like to ask all three presenters now to switch the cameras on, and we'll have a look at some of the questions, and please, as we're proceeding through answering the questions, please post any further questions that you have, and I'm sure our presenters will be very happy to provide you with responses. So the first question that we have is probably directed towards Ryan, and it's please comment on the role of nuclear power for providing the energy to meet the demand for hydrogen. That comes from David Glover.
Sorry, give the nuclear energy to sorry,
for providing energy to meet the demand for hydrogen. So I guess that possibly in place of using wind power, to using nuclear.
Yeah, I think in terms of nuclear as an option at the moment, the nuclear option, I mean, even in my slide pack, in terms of as it is today and usability of nuclear as an option, regardless of the environmental credentials of nuclear, in terms of bang for your buck for nuclear and infrastructure, needed to effectively power UK through nuclear as an option, there's this disproportionate financing around that in terms of how much would the nuclear option cost compared to a hydrogen option that is actually viable. So if it's for nuclear generation for electrolysis, it's probably a wider debate, and we could talk about some of those options. But ultimately, if you look at the chart in terms of just generation alone in the UK, for nuclear, it's really down. I think today it was only like 2%, if that, in terms of UK power being produced by. No, sorry, I think it was 12%. Sorry, I'm discrediting nuclear, but that's where it currently sits at the moment. So then to upscale that to cover the heat demand, I don't know how viable it is as a permanent net zero solution.
Right. Okay. Thanks, Ryan. The next question we have is from Stephen Argles, who asks, and perhaps this is one for Stephen, when you produce hydrogen from water, what happens to the oxygen?
Yeah, thanks. That's a good question. So we are not currently storing the oxygen on site, but we have indicated in our planning submission that we might take that option up in the future as we expand into the area and move into the whole systems, because there's obviously uses for oxygen, but right now it's been vented, but going forward we've got nearby local hospitals, etc., that could potentially be involved in the whole systems network. So the short answer is it's venting it just now, but we have plans in the future to utilize that and store that.
Okay, thank you. A couple of questions from me that I was interested in. You mentioned, Stephen, in your presentation that the existing or the new pipeline system you're putting in was relatively low pressure, and I just wondered if there was, in using hydrogen, could you use a higher pressure, or is it intended to use a higher pressure to transport it longer distances as you do with natural gas, using medium pressure and even high pressure pipelines?
Yep, certainly that is the plan. So there's a whole network of projects being undertaken by us and by others, and we're looking at pipelines for hydrogen right down from the NTS. We've got an LTS project as well, and we're looking at all pressure tiers in the distribution network. So that's not just SGN, that's across all the GDMs. So that's definitely the future model that we're looking at.
And then obviously, again, you've laid a brand new network, and I guess that's really to give customers choice. But going forward, how much work will probably be needed on the existing network, bearing in mind that there's still a multitude of different materials, and is there a lot of work to do, or will hydrogen be able to be used within the existing system without too much work?
So the final list of interventions on the networks is still being worked on. So what we're doing is it's kind of iterative, as you know, 805 knows what it needs to know for what we are doing. As we go forward to small conversion on phase 2 of 805, when we might add some of the local gas network onto the hydrogen network, we'll know what interventions are needed there. But other projects, Northern Gas Networks H21 project, they've already done quite a lot of work looking at existing assets, and we've supplied them with lots of assets that have been dug up and tested, and largely what we're finding, same as what we found in our own network, is that if it's gas type for one gas, it's gas type for the other. But it's, as I say, it's a sort of iterative process through this gas grows green trial, where you collect the safety and evidence first, then you move on to that next phase of the trial, and you keep doing that as you go.
Okay, we've got a question from David, is it Haig, who asks, why is it more efficient to transport hydrogen than it is to simply heat water in the home using electric? Is it an issue of capacity on the grid, or is hydrogen electrolysis more efficient outright than electric heating?
I mean, it's not something I would claim to be an expert on, but the efficiency of the fuel that we're using depends on a number of things. It depends on where the electricity comes from, the efficiency of the electrolyzer. So the efficiency of that versus whatever the alternative electricity option would be something that you would look at there. But in general, transporting electricity has much larger losses than transporting a gas, whether the gas is hydrogen or whether it's natural gas. I don't know if Ryan wants to jump in on that, but
I think as well the important point is, and I was kind of raising it in the presentation, it's for the customer as well. So, you know, in terms of the customer using at the domestic level, then that's a significantly hike in price for the customer to produce something that they're already getting from their gas supply. So in terms of customer is king in this situation, and you know, we can't necessarily leave people behind in terms of that option. So we have to, you know, hydrogen, it becomes an economy in terms of the carbon pricing for hydrogen of the future. It's going to actually break even to make it actually a really cheap fuel, because everything's going to be levied on carbon. So, you know, it will come to that point where our trading price for hydrogen is significantly low, that's going to be similar, if not identical, to what the current pricing is today. So if you're looking at, you know, 14 pence per kilowatt hour of electricity, but relative price for gas is, you know, between 2 to 4 pence, you know, that's one of the main drivers for it as well, in terms of delivery. 100% energy that goes in the system comes out the system, whereas there's degradation across electricity as well, which is costed and factored into the electricity networks pricing as well.
Thank you. We've got one more question here for you guys on hydrogen, and then I've got a couple of questions for Ali. So, is there a viable option for green hydrogen to be used as energy storage in place of battery electric storage?
Yes.
Yes.
I think so. I mean, it's really, for us at the moment, looking at it, it's that option is there in terms of storage medium. Any type of hydrogen is on the. It really depends on its use for the hydrogen. So, what are you going to use that hydrogen in application-wise? So, for instance, if it's hydrogen fuel cells, then there's, you know, it really needs a sort of pure hydrogen to go into those. So, you're talking about filtration of systems and how you can get a purer hydrogen into those types of fuel cells. So there is a bit of kind of front end designing work for application, depending on what it is. But ultimately, yes, that is the answer to that question.
Okay, I'll now move on to Ali and a couple of questions for him. The first one comes from Amir, and it's can you use the robotic system to carry out inspection of the welds in PE pipes? Yeah, you muted, Ali.
So sorry.
Yeah, no problem.
Yes, I think so. That was the actual goal of developing this robotic system, is for other companies to come back with their requirements and needs, and we would be able to easily integrate different tools into the system. One of the things I want to mention is what we have done is these robotic arms have very high precision as far as their movements. They have very accurate sensing capabilities. So traditionally, they were the best thing ever in a manufacturing environment. But the challenge was, like, once you bring that out of the manufacturing environment, once you unbolt it from the ground and then take it somewhere else, how do you recalibrate everything efficiently so that you would be able to carry out the same precise work in an unknown environment? What we have done is we basically created a system that can come to a new environment using all the perception and information that's available to be captured from the environment. We are calibrating everything, and then the robot arm can do the same precise work. So applications like weld inspection is definitely something we can work on.
Right. I'd just like to ask you about, well, first of all, the scanning tools that you have, and are they capable of differentiating between pipes of different materials, such as metallic and plastic and clay and concrete? Is there no issues with that?
To some extent, it's possible. Using ground penetrating radar, you can easily differentiate plastic from metallic pieces. But what is necessary to happen is we need to deploy this robot in different environments and collect a lot of data, and using machine learning, we can train models that can look at the raw data. So what we are capable of doing right now is process everything on the spot using our accurate localization information that we have, and then adding on more techniques for differentiating, or for example, different material is also a possibility that can be done after collecting a good diverse data set from different parts of the United Kingdom, for example.
Yeah. And then just thinking about the excavation and that, are there any restrictions on the type of soils that can be used in, or obviously we've a wide range here in terms of clays and sands, etc.
So what we have developed under the project is a technique that integrates supersonic air nozzles into the excavator head that allows the operators to stay away from the excavation site, and the robot autonomously goes through everything. There are two pieces to the excavation. One is the agitation of the soil, and then the second piece is vacuuming out everything that's been agitated. And dealing with, for example, wet clay is like one of the big challenges in the industry, in the vac truck industry. And there are different units that some are very capable and successful in removing moist clay, some are not as much. Yeah. What we have done is we have created almost like a VacX agnostic system. So we are agitating the soil, and then we are able to integrate any type of VacX unit into the robotic arm so that we would be able to effectively remove the soil that's been agitated.
Oh, that's great. And then, perhaps my final sort of question around this is about the surface itself. You did show on the video that you were using it through asphalt and then concrete, but are there any issues then? Most of the roads in this country have then got road base with stone and what have you, and then going into soil. Are there any issues there in terms of the cutting capabilities?
So these are all to be tested. What we really try to validate and design the robot with is one of the most aggressive environment that potentially that chainsaw would get exposed to, and this is reinforced concrete overlaid with asphalt. Obviously, that chainsaw can cut through different material. Now the question is, what would the integrity of that block would be after it's cut in a core? Is it gonna just crumble and not come out as one piece, or we would be able to potentially make different shapes and forms? These are to be tested, and then I guess after all of our field trials in the UK, we're hoping to come up with some type of report that shows the performance of the system in different environments, possibly separating that by different parts of the country, because I know the road surface and the soil condition is different in different parts of the country.
Okay, guys, I think we've more or less come to the end of it. I would say about that robotic tool, it's in my view fabulous, and having worked in this industry for over 40 years, and the accidents that that everybody's seen, through nobody's, just minor carelessness, and that this can just take all that away and protect people when they're working on this type of maintenance. I just think it's a real step forward, and I do wish you all the best with it, and I hope these trials are successful over here. So thank you so much. Okay, as I said, we've come to the end of the questions now, and I hope you'll all agree with me that we've had a really good session this afternoon, and I'd like to thank our guest speakers for taking the time out of their busy schedules to provide us with such interesting and thought-provoking presentations today, and these presentations have certainly provided us with an understanding, first of all, of the impact that hydrogen can make on our road to net zero through the decarbonisation of our gas pipeline networks. And then also, we've heard how robotics can revolutionise inspection and maintenance repair of our underground infrastructure. So, both of these innovative moves forward will certainly help us to meet our challenges of climate change and reduction of environmental impacts of our activities into the future. So now I'd just like to take a quick moment to provide a couple of thank yous. I'd first like to thank Kate and Catherine at Guild HQ and Lynn at UKSTT's HQ for their hard work in organising this event. And I'd also like to thank Alice and the team at Westrade for hosting the event on the GoTo platform. I have to say it's been pretty seamless, and I've been really happy with how it's all gone forward. So that now concludes our webinar. I'd like to thank you all for attending and supporting the Green Alliance. And if you'd like to be involved with the Green Alliance and to discuss a presentation or sponsorship opportunities, then please make contact with Lynn McLachlan at UKSTT or Kate Byfield at the Pipeline Industries Guild, and I'm sure they'll be able to help you with that. I'd also like you to look out for our posts via email and on our websites and social media for our future program. Our next event is on the 22nd of June, when we have Simon Farris of Severn Trent Water, who's going to provide us with a presentation on Severn Trent's approach to the challenge of reaching net zero and the generation and use of sustainable energy. And just to finally say that all of today's attendees will receive a link tomorrow to that webinar. So I hope you'll find time to put it in your calendar so you can join with us. And then finally, we do value your feedback on all our events, whether that be good or bad. So please please provide that to us. And also we're happy to receive ideas from you and what we should have in our program going forward. And we're always happy to speak with our members, so please do not hesitate to contact us at either Guild or UKSTT HQs. So thank you again for your support and attending this event, and I look forward to hopefully meeting you at some point in the near future. So thanks again, everybody, and good afternoon. I hope you have a nice evening. Bye.
Thanks.
Thank you.